some important concepts in fluid dynamics, and they don't appear too much in this course, but they're important to know about. And the first thing is to just try to understand when surface tension might be important. We'll find that in your homework and in Chapter 3 and beyond that there can be what's called capillary rise inside tubes. Water has a tendency to wick or adhere to materials. It depends on the material, the degree to how much they adhere, and it depends on the kind of the liquid and solid interface. So we can get capillary rise, and that can contribute to error in measurements when we're trying to measure things like pressure using pressure taps and so forth, which we'll talk about later. Also, there's some phenomena. There's a big list of these right at the head of the section 2.8, but some of the other important things are, for instance, capillary instability, when you might have a liquid jet coming out of a piece of industrial equipment that might be breaking up into droplets. The droplets will have a surface tension associated with them, and so forth. Also, detergents have an effect on surface tension, and therefore they're used in order to help remove dirt from clothes and other materials. So let's just go forward. There's two ways to view surface tension. One is that surface tension is like a stretched membrane. There's a really nice figure, and I'm just going to try to repeat it here. I should have put it in the notes, but there's a really nice figure in the book that shows the molecules at the surface of a fluid. And if it's in kind of a lattice, this was a little oversimplification, but it's showing the force of attraction of these molecules to each other. And the ones on the surface are drawn down towards into the liquid, whereas the molecules inside the liquid are equally drawn in every direction by the molecules around them. So the surface is a special case of a fluid, and in fact, as I mentioned, the key point here is that these molecules are being drawn down into the liquid, so it's like a stretched membrane. And we can describe that phenomenon as surface tension, and we can do it either as a force per unit length along that interface, or we can think of it as an increase in the surface area and the energy required to basically increase that surface per unit area. Now look at how the units work out. The units of this are force per unit length, so the units of sigma are going to be Newton times a meter. But what happens if we multiply both the top and the bottom by a meter? We get joules per area, joules per meter squared. And so in one case, we have this unit applying to the energy concept, that we can think of surface tension as increasing the surface area of a liquid. Or in the other sense, we can think of this as a force per unit length along the interface. So there's kind of two ways to think about it. For the most part, we'll use this idea, the top one. This just mentions that there's sometimes there's a dependence of this with temperature. So in some certain instances, you may need to take this into account. For the most part, we'll use this value that's shown here, 0.0728 Newton per meter, for calculations in this class. Although there may be an instance when you'll have to look it up for your particular fluid. Now, the major concept here is that there's I wouldn't call it a battle, but there's a a push a tendency for materials to for liquids to adhere to materials that they're setting on. And so there's a battle between adhesion and cohesion. Adhesion is the process where the liquid is adhering to the material. And you can see in this case where we have water on glass, the liquid water droplet is adhering to the glass and it's spreading out. And so that's what's being shown here on the left. Over here, we're being shown that the cohesive force is weaker than this adhesion force. The cohesive force is what actually keeps the liquid particle together as a droplet and would maintain its spherical shape. So in this case, the cohesive force is less than the adhesion. And in this case, where we have water beating up on what's called a hydrophobic material, such as Teflon, so now this is a Teflon surface rather than a glass surface, we see that the water droplet is maintaining its spherical shape. It's just sitting on top of the Teflon almost. It's interesting to note that many of you probably have Gore-Tex clothing for outdoors. Usually Gore-Tex shells are used for rain gear, and there's a Teflon membrane inside Gore-Tex. At least there was many years ago when it first came out. There was a thin strip of Teflon in there inside, in between two layers of material that were designed to beat up the water so that the water would not wick onto the clothing and would therefore ball up and just fall off the clothing, and thereby keeping you dry. So we can see that this is going to depend on the liquid properties and the solid properties on which the droplets are forming, and it's going to be a balance or basically a battle between adhesion and cohesion. Again, adhesion is how the material adheres to how the liquid adheres to the material, and in the case of glass, it's quite effective. In the case of Teflon, it's not very effective, versus cohesion, which is the force that keeps the liquid molecules together. So one of the ramifications of this is capillary action, and you'll be dealing with this in your homework. Capillary action, when we have these forces, these adhesion forces, if you have a glass pipe, if this force is great enough, it can actually draw against the weight of the fluid. Basically, it can draw the fluid up into the pipe. And so so there's two different cases. You can have capillary rise in the case of water and glass, or in the case of capillary repulsion with mercury in glass, you can actually have it go down. Now, I believe that in this case, if I draw on this, that the inside of the tube actually in this case will look like this, because the material, the liquid, is kind of going up the sides of it. And in the case of the repulsion case, down inside the tube, I believe it would actually be like this, because the repulsion is actually drawing the liquid back down into the fluid. So, but the main point is that you can determine the effect of the surface tension. You've got to eventually have a balance. This thing will come into, it will move, and then it will come into balance, where the weight of the fluid that's being drawn up in terms of capillary rise, the weight of this fluid above the surface level, the weight of that column, needs to equal the surface tension force. In other words, the surface tension has to basically pull up that amount of weight. And once it all comes to a static situation, these two forces will be equal. And what you can do is then write down the weight here, which we have gamma. Remember, this is rho times g times the volume. That will give us basically mg. So rho g times the volume is the weight, mg, and that this is the surface tension force, which is the surface tension coefficient, sigma, times the length of the fluid and times something called the contact angle. Now, if we there's some good pictures in the book. Actually, this also shows the contact angle here, theta, which is basically the angle between the material and the liquid, and that the angle that makes. And you can see in the case of when it's a very hydrophobic material, that contact angle is very large, and when it's a very a material that where there's lots of adhesion, the angle will be very small. And so to maximize this, to look at the maximum condition, we normally, or we can set theta equal to 0, where it would mean that the water droplet had completely adhered to the material. And so you can basically, putting in theta equals 0 makes cosine theta equal to 1, and then solving for delta H, we get the rise of the fluid into the tube. And basically this is the equation you'll be using in your homework to determine the capillary rise. Actually, I think you're actually asked to determine the diameter for a given capillary rise. So there's a couple things we can do. There's many things we can do with this. One of them is to it says applying force equilibrium to calculate the pressure rise inside a droplet. And this it says the pressure inside a water droplet is higher than the pressure of the surroundings. Determine a formula for this pressure rise, and then calculate the pressure rise for a 2 millimeter diameter water droplet using this factor that we saw before. This is actually just equal to 0.0728 Newton meters. They just changed the units to be millinewtons here. So it's the same type of, it's the same coefficient of surface tension that we've used before. So let's just go ahead and do that. The surface tension force is just equal to sigma times this L. L for this problem is the length of the surface, which in fact is the diameter. I'm sorry, the circumference of the circle, which is pi d. And the pressure force for this is just a pressure, the force. Let's just do it this way. The pressure is just a force per unit area. So the pressure force is just going to be pressure times area. Pressure is what we want. The area of the droplet is just pi d squared over 4. So we're going to have, for this case, this is going to be pressure pi d squared over 4. And we can set these two forces equal. The force per unit, basically the force of the pressure inside the droplet and that of the surface tension. And we can solve that. This is example, as I showed you before, this is example 2.4 in the book. I'm kind of going through this quickly, but you can read this in the chapter. So if we set these two things equal, oops, we have pressure pi d squared over 4 is going to equal sigma pi d. The pi's cancel out. One of the d's cancels out, and you're left with a fairly simple formula for the pressure. The pressure is going to be equal to 4 sigma over d. And we can just plug in the values that the book has given for this problem. We can, 4 is just a constant, obviously. We can plug in 0.0728 newtons per meter for the surface tension coefficient sigma, and then just the diameter of the droplet, which was 2 millimeters. And you can see that we have, through the grid method, our units actually turn out to be Newton per meter squared. By this time, this ought to be starting to look quite a bit like a Pascal. because it is 1 Pascal. Remember, 1 Pascal equals 1 Newton meter squared. So we can make that conversion in a minute. And the units, or I'm sorry, the numbers that come out of this, if we multiply them out, are 146. So if this cancels that, we're left with 146 pascals for the pressure. Okay, so just finding out what basically what the pressure inside the droplet has to be in order to, as a result of the surface tension effect of the drop being held together by this cohesion force. So the next problem is to look at, this is a really interesting problem, that you can take because of this stretch membrane of the surface of water, you can take a light object such as a needle, and you can lay it on top of the water, and the water will hold the needle in place on the surface. Some insects use this for, like water skippers will use this as they travel across water and stay on the surface without falling in. And so they have a very high cohesion between basically their feet and the liquid surface. So let's go ahead and look at this. It says the internet shows examples of sewing needles that appear to be floating on top of water. And in fact they are. This effect is due to surface tension supporting the needle. Determine the largest diameter sewing needle that can be supported by water. Assume that the needle is stainless steel and has a specific gravity of 7.7. So, so what we basically need to do here is calculate the force balance between the surface tension, which for this case is sigma 2 times L cosine theta. This is, you can look in the book for the diagram of this, but let me draw that again. My apologies. Cosine of theta. This is basically the length of the surface again, of the surface, and or the needle, the length of the needle surface that's in contact with the liquid. And in addition, we need to set that equal to the weight of the needle, which is going to be, mg, but we can write that again as gamma of stainless steel times the area, times basically the volume. Remember, this is rho g. This equals rho times g, and that equals m over the volume times g. So if we take this times the volume of the needle, we get mg. So that becomes the gamma of the stainless steel times we're going to approximate this as a cylinder, so this is going to be pi d squared over 4. Basically it's a cylinder that looks like this. And so this is the diameter, and this is the length L going along here. And so we have L. And so we can set these two things equal, and we have sigma 2L. We're going to again set the cosine to be equal to 0 to maximize this effect, assuming we have kind of perfect adhesion. So this thing, theta equals 0 gives cosine of theta equal 1. So we've got a 1 here. And we're going to have gamma SS pi d squared over 4 L. The L's cancel, interestingly. And if we solve for D, we're going to get D equals, we've got a square, so we're going to move the 4 over to the other side where we have 8 sigma. And then when we divide by pi gamma s, we're going to take the square root of all that. So this is our equation for the diameter, the maximum diameter that we can have of a needle um, that will stay on the surface. And note that it does not depend on the length of the needle. It only depends on the diameter, because that's really what's determining the amount of liquid that's in contact with the needle. So when we solve for this, we're going to have the square root of 8 times 0.00728 Newton. I did that wrong. I got an extra zero in there, 728 Newton meter. Again, that's the force per unit length. And that's going to be divided by pi. Let me just remind myself here. Yeah, pi times the gamma of stainless steel. So this is pi, and I looked up the gamma of stainless steel, and it's 75.5 times 10 to the 3, and gammas are newtons per meter cubed. So we can see that the units are going to be newtons, and one of these meters cancels one of these. We're left with 2, so we're actually left in the numerator with meters squared. And out of this we get, actually don't have this written down in my notes, but this is going to be 1.57 squared is the answer. We're going to take the, actually that's not, let's see, it's a smaller number than that. I actually don't have the number in front of me right now for how this works out. I don't have a way I can quickly calculate it, but if you can see that this is going to be in meters squared. If we put the answer in millimeters, because it's very small, the answer is going to come out to be 1.57 millimeters. So basically, let me recap that. If we take 8 times the sigma 0.0728 divided by pi times 75.5 times 10 to the 3, that's going to be a pretty small number. And the units, we're going to take the square root of that, and the units are going to be in meters squared. So we have to take the square root of all that, and then the final units are in meters. And if we convert them to millimeters, we get this for our answer. Okay. So we can have a fairly large size pin that can be supported on water by the surface temperature, the stretched membrane of the surface. So that's basically what I wanted to say about surface tension. I think the main point here to note is really capillary rise. This is the thing that you're going to be using in your homework, and to have an understanding of how these effects occur because of basically the molecular forces that keep the surface of a liquid together. That's really this is hard stuff to understand, but conceptually that's what surface tension is. Now, kind of an equally difficult thing to understand is the issue of vapor pressure. And this actually becomes pretty important. I think I can explain this pretty straightforwardly, but it turns out that a liquid, under the right conditions, you can make a liquid vaporize. This happens all the time in clouds. We have liquid water droplets, and if we warm that cloud, the liquid water droplets will evaporate. And so, and also we have evaporation all the time from lakes and the ocean, especially in the tropics when it's where it's nice and hot. So we know that we can have phase changes between liquid and gas. Another good example is when you form a cloud. Water vapor exists in air at all times everywhere on Earth. And when that vapor pressure actually exceeds what's called the saturation vapor pressure, which I'll show you in a minute, a graph of in a minute, that condensation is going to occur. You're going to start to you're going to basically cool down the air enough and create relative humidity of 100% so that the water molecules start to adhere to each other. And when this happens, water droplets will begin to form cloud particles. So we've got in the book, this is a very short section, but this is actually a really important point for fluid dynamics, because you can cause something called cavitation out of this, which we'll talk about later. Cavitation can occur when you have a liquid. We can see here that when we're above this line, when the pressure is above this line, when the conditions that, let me say the pressure and temperature conditions are above this blue line, we will have a liquid. But when we go below the line, the liquid will vaporize. So imagine we're in a pipe, and I'm going to grab my red pencil here. Imagine we're in a pipe and we're sitting here at 30 degrees C and we're at high pressure. There's a high pressure pipe and we're sitting at this point here. What if something causes the pressure to decrease very rapidly? We will talk about how things like this can occur when we're talking about pipe flow. If the pressure decreases really rapidly, we can cause that liquid to vaporize inside the pipe, and that can be a very dangerous situation for the pipe. Everybody can, sometimes you can hear pipes popping and hissing and making noises inside them. Normally that's cavitation. And what that can do is it can cause destruction of the pipe material. So this is a very important point. Now the flip side of this is, what if you were down here? What if you were in the vapor phase, as I said? What if you were just water vapor in the air? And you were, let me do that a little bit differently. Let me just say we're up here. Let's say we have some water up here, and we just cooled the air down. Say we're in the tropics, and we cool the air down. That air would be pretty hot for even the tropics. But if we cooled the air down without even changing the pressure, we could cause liquid droplets to form. And this might be the situation. Actually, right when it hits this line, we will get a cloud forming. So there are many different processes that can occur going through this phase change. And basically this line right here, this blue line, is the line of phase change. When you're above the line, you're liquid, and when you're below the line, you're a vapor. And I just put another graph here from a meteorology textbook, which shows it better. This shows the fact that this graph shows, you can see here that this is a log scale over here, and I don't think that was really presented very well in the book, but you can see when it's plotted on a linear scale, you can see that this effect, this vapor pressure, the saturation vapor pressure, or kind of the phase change line, is exponential. So it's a very important effect. So that's it for what I had. I believe that's it. Yep, that's it for chapter 2. So hopefully we have a better understanding